Welcome to Study Loop.
It is given a regenerative gas refrigeration cycle using air as a working fluid. We have to find effectiveness of the regenerator, effectiveness of regenerator. In second part, we have to find rate of removal of heat from the refrigerated space. Third, coefficient of performance of refrigeration. D, refrigeration load. And coefficient of performance if this system is to be operated on a simple gas refrigeration cycle. Let us start solving it. Properties of air, this is to be used. Specific heat at constant pressure 1.005 kilojoule per kg per Kelvin, and adiabatic gas constant 1.4. Using, just a moment please. Using adiabatic relation between temperature and pressure. Temperature of the fluid in adiabatic process in second step is T1 into P2 upon P1 to the power K minus 1 upon K. Substitute the value. Temperature T1 is given 273.2 Kelvin. Pressure compression ratio is given 5 in the problem. Value of K is 1.4. So 1.4 minus 1 divided by 1.4. So you will get 432. 0.4 Kelvin. Carnot efficiency of the cycle is defined as enthalpy of the fluid in second state for adiabatic process minus enthalpy in state 1 upon enthalpy in second state minus enthalpy in the first step. Efficiency is given 80%, so this is 0.8. Enthalpy in adiabatic process of second step is 432.4 minus, just a moment. First, let me convert it into temperature relation. So it can be written as temperature 2Ts minus T1 upon T2 minus T1. So we can write 0.8 to be equal to 432.4 minus 273.2 divided by T2 minus 273.2. So on solving it, temperature at second state we will get 472.5. Temperature at 4 state can be determined again by temperature pressure relation for adiabatic process. It is defined as P5 upon P4 whole to the power K minus 1 upon K. Substitute the value. P4 into pressure compression ratio is 1 by 5 upon 1.4 minus 1 upon so this can be written as temperature of fifth state in adiabatic process to be T4 into 1 upon 5 whole to the power 0.4 divided by 1.4. Now, efficiency of the turbine can be defined as H4 minus H5 upon H4 minus H5 in adiabatic process. Efficiency is given. You may convert in temperature T4 minus T5 divided by T4 minus T5s. Efficiency is given. Turbine efficiency is given 85%. So it is to be 0.85 to be equal to T4 we are measuring. Temperature T5 is given 193.2. This is given in the problem. T4 we are measuring, that is T4 into 1 upon 5 to the power 0.4 divided by 1.4. On solving it, T4 you will get 281.3. Kelvin. Effectiveness of the regenerator. First, we have to find temperature of the sixth state by applying energy balance on regenerator. So applying energy balance at regenerator. Mass flow rate of the fluid into specific heat to changing temperature from third to fourth state is equal to mass flow rate into specific heat into changing temperature from first to sixth state. So from here, temperature of sixth state you will get T6 to be equal to T1 minus T3 plus T4. On substituting the value, we will get the temperature of the fluid at sixth state, and it is to be T1 having the value 273.2 minus 308.2 plus 281.3, that is 246.3 Kelvin. So effectiveness of a regenerator can be defined as H3 minus H4 upon H3 minus H6, that is, in terms of temperature you may write T3 minus T4 divided by T3 minus T6. Now substituting the value, T3 having the value 281, sorry, 308.2 minus T4, that is 281.3 upon 308.2 minus 246.3. So effectiveness we will get 0.434. This is the answer of part A. For part B, refrigeration load can be defined as rate flow rate of the fluid specific heat into T6 minus T5. Mass flow rate is given in the problem, 0.4 kg per second. Specific heat 1.005 kilojoule per kg per Kelvin. Change in temperature at the sixth state temperature of the fluid is 246.3 minus 193.2. So refrigeration load we will get 21.36 kilowatt. C. Power input of compression, mass flow rate, specific heat of air into changing temperature from first to second state, that is T2 minus T1. Mass flow rate is 0.4 kg. Specific heat is 1.005. Change in temperature from first to second state 472.5 minus 273.2. On solving it, you will get input power of compressor to be 80.13 kilowatt. Now output power of turbine, mass flow rate into specific heat of air into change in temperature from fourth to fifth state, so T4 minus T5. Mass flow rate is given 0.4 kg per second. Specific heat of air 1.005. Change in temperature from fourth to fifth state, you will get 281.3 minus 193.2. So it is to be 35.43 kilowatt. Hence coefficient of performance you will get refrigeration load upon total work input, power input. Now substitute the value. Load of refrigeration is 21.36 kilowatt per second. Net work done will be work done by compressor minus work done by turbine. So that is 80.13 minus 35.43. So on solving it, it is to be 0.478. If the simple refrigeration cycle is to be used, then temperature of fourth state in isentropic process can be written as T3 into pressure compression ratio whole to the power K minus 1 divided by K. T3 is given 308.2 into compression ratio is 5. So 1 upon 5 whole to the power 0.4 upon 1.4. So temperature of fourth state in isentropic process you will get 194.6 Kelvin. So efficiency of turbine we can write T3 minus T4 upon T3 minus temperature of fourth state in isentropic process. Now substitute the value. Efficiency is given. Efficiency of turbine is given 85%, that is 0.85. Temperature at third state is given 308.2 minus T4 upon 308.2 minus temperature of fourth state, that is 194. Fourth state in isentropic process of 194.6. So temperature of fourth state you will get 211.6. Now the heat transfer at low temperature, rate of heat transfer at low temperature will be mass flow rate into specific heat change in temperature from second to first state, that is T2 minus T1. Mass flow rate is given 0.4 kg per second. Specific heat is 1.005. Change in temperature is, let me correct it, change in temperature from first to fourth, 1 and 4. At first state, its temperature is 273.2, and in fourth state it is to be 211.6. So you will get 24.74 kilowatt. Now we have to find the coefficient of performance if it is to be used as a simple refrigeration cycle. So first we need to calculate net power input. It is to be equal to power input to compressor, which is defined as mass flow rate, specific heat into change in temperature from second to first state, that is T2 minus T1, minus power output of turbine, mass flow rate into specific heat into change in temperature from third to fourth state, that is T3 minus T4. You know all the parameter. After substituting the value, you will get 41.32 kilowatt. I have not shown here the calculation, that easily you can do it. All the parameters are given above, just you have to substitute it and you will get. Now coefficient of performance, amount rate of absorbing the heat at low temperature upon net work done, net power input, you may say, putting the value, all the parameters are given above. If you substitute, you will get the coefficient of performance to be 0.509. That's all for this problem. Thanks for watching it.